Okay, so good morning, everybody. My name is Angela Dalkey, and I'm from ACEMS, an ARC Centre of Excellence for Mathematical and Statistical Frontiers. And together with QT's Centre for Data Science, we've hosted a first in, we hope, a series of talks on the topic or theme of explainability in data science, including AI and machine learning. So before we begin, I would like to acknowledge first the traditional owners across Australia from wherever you're joining us today, and pay my respects to their elders past, present and emerging. I would also like to give a very warm welcome to our guest speakers for today. You've read about their wonderful, hello, I can see both there. You've heard about their wonderful credentials, and they'll be giving a talk on explainable analytics for black box machine intelligence. And this topic is of interest not only to academics, who I've seen a range of people sign up, but also to industry. So we look forward to their talk. It will be a 45-minute presentation, and following that, there'll be time for Q&A and plenty of discussion. So please feel free to pop your questions in the chat box, or also unmute yourself at the end, and feel free to ask questions. Also, for those who do have some expertise in relation to the theme of explainability in data science, please do send me an email or a message. Angela Dalkey, you can find me on the QT mailing system. We would love to hear from more speakers as part of this series, because it is of such great interest. So without further ado, I would like to mute myself and ask others if you could do the same, and I will hand over to our speakers. Thank you. And yes, if everyone could just mute yourself. This is being recorded for those that can't come from industry today. Thanks very much. Over to you.
Okay, thank you very much, Angela, for the introduction, and good morning, everyone. So Angela, maybe can we share the screen from this end? Yeah, we can do that now. So I just want to first check if everybody can see the screen. Did I share the right screen?
Looks good.
Okay, great. Okay, so yeah, thank you everybody for your interest in attending our talk. And very quick about myself. My name is Chun. I'm a senior lecturer in the School of Information Systems. And in the past decade, I've been really passionate in working on process mining, which is process-oriented data mining, try to extract knowledge and insights from event logs, capturing process execution to help with process improvement and support business decision making. Then in the recent years, I started to get a bit curious about the certain, machine learning and predictive models, that how do they make the certain predictions. So I started to get quite checked into the explainable analytics, and again, working in the context of predictive process analytics. And yeah, so I will now just hand over to Kat, give a quick intro herself.
So hello, everyone. My name is Catarina Moreira. I am a lecturer at the School of Information Systems, where I'm also the deputy HDR academic lead. Before coming to QT, I was also a lecturer in finance at the School of Business in the University of Leicester in United Kingdom. So I have always been very passionate about machine learning and decision theory. So my research is very focused in cognitive models and decision models. And now I started to be very passionate again about this field of trying to demystify these black boxes from the literature. So yeah, that's me.
Okay, great, thank you. And yeah, just very quick agenda for today, as we mentioned in the abstract, that we're going to give a very quick overview of the black box machine learning problems and explainable artificial intelligence, we call it XAI. Then we're going to share, each of us going to share with two pieces of our recent research. And then we'll conclude the talk with some open research challenges. It's open list, and hopefully to guide us a way ahead. So the first one, can we really nowadays, when the machine learning, deep learning becomes more and more smart, are human ready to trust and accept the decisions? So I think machine learning, deep learning, we can't stop the evolvement. People love to see the 90% of accuracy or 98% of accuracy, but at the same time, people also realize that these machine learning models, they becomes more and more sophisticated. So almost lead to a black box model where they take the data as the input, you feed in the data, you get the results, and it's autonomous machine learning results. Are we ready as a human? Are we ready to take them? So here are some of the examples that I actually used as quite pretty early examples to raise this problem with black box machine learning models and to promote and motivate the need for an explanation of these black boxes. So if you see on the right-hand side, it's a predictive model to tell the picture of in the image whether there is a husky, the face of husky, or a face of a wolf. And the model is highly accurate. If I'm not wrong, I think it's almost like 98% of accuracy. But when the researchers dig into deeper to understand what has been used to make these predictions, and what they found is actually they use the snow in the background to adjust, to make that decision. So basically a snow on the background used to make the prediction, but usually Siberian husky is in this winter, a Siberian forest, and then that is highly, relevant for these features. That's why it leads to a high accuracy. Then the example on the left-hand side is another example of looking at the prediction of a pneumonia and diagnosis, where instead of using the pathology information, they found they actually using a metal token in this X-ray image to tell whether there is a diagnosis of pneumonia. So what these tells us that predictions can be quite accurate. However, the reasoning behind these predictions may not be incorrect, may not be correct. And another example is also, I believe this is also well known, is this is a decision system that's used in US court to decide or to determine the risk factors for criminals. And what people have found is still a black box, and people still don't know what data they have used to fit the black box. But what people have found out later on is that this decision system is highly biased between different races. For example, the criminal on the left-hand side is, of course, from a white, people, and it has a quite strong prior offenses, and they also find that they lead to subsequent more serious offenses later on, where only give a low risk of 3, where the people on the right-hand side have a high risk of 8. But if you look at the prior offenses and subsequent offenses, it's actually a lot less serious than the one on the left-hand side. So, but this person on the right-hand side is given high risk as being judged by the system. So clearly there is a serious bias, happening in that machine learning or the machine-based decision-making system. So just as a summary, having a black box machine learning system is quite dangerous. It can lead us to making wrong decisions if we fully trust them. It can also reinforce some of bias in the data, and it can, promote gender and race discriminations. So as we know that the European GDPR come into effect in 2018, it is then compulsory that the individual end users have the right to demand an explanation of how an AI system made a decision that affects them. So this is not just to motivate us to have a explanation, but it becomes more and more as a compulsory. So some very interesting insights that we share with you based on a recent literature review that we did in the area of XAI and also causability and counterfactual, Catarina will also talk about later on, is that we look at the literature in the XAI or machine learning, the machine learning, AI, machine learning, deep learning. And what we found that there is quite interesting shifts that we can find that back to 2012, where you can see that a lot of literature years, they very much focus on a machine-based learning, like pattern recognition, computer-aided diagnosis. And when it moved on to 2016, when this need for GDPR start to be raised, and then people start to consider the human factors into this decision-making and this learning system. And later on to 2018, and then you will also see that, again, the learning systems start to involve both human and the machine. And now in recent years, now 2020, 2021, the explainable AI becomes a focus of the area. So just as a quick summary, black box problem, as we say, if we feed the data into a black box, it could be very much from already the data wrangling, encoding, and then the predictive, machine learning, deep learning model, and come up with a prediction. But the question for the end user is that with only knowing the prediction, do we know why did the system work or not work? Can we trust these results? Is the system valid, or is there an error? And then if there is, how do we correct them? So the principle of XAI approach is basically to say that we now take these questions from the end users, and then let's demystify the black boxes to generate explanations that will be aiming for address the questions from the end users. And ideally, we would like to bring this explanation through a proper user-friendly representation or interface to then so that the explanation not only become not only become user understandable, but become believable and persuasive. All right, so I guess that's a quick view of the area. And now let's move on to our first topic, which is XAI-enabled model inspection. And we would like to talk about this in the context of predictive process analytics. And of course, the first thing is that, let me give you a very quick intro to process analytics, where the process analytics focuses on analyzing event logs to extract insights about the actual evidence-based process behavior performance for bringing inputs to objective inputs into business decision-making. So an event log, usually we ask, what is event log? And event log captures the historical execution of business processes. And here the idea of, so this is a simplified example of a hospital visiting process. And the idea here is to show you that a process, not just looking at the sequence of activities, we're also looking at these activities can come in the different sequences for different patients. And for such a simplified model, it can be hundreds of patients visiting the hospital every day. And this will come to hundreds of instances of these patient, episodes of patient visiting the hospital. And of course, the sequence will be different if we also start to take into account which medical staff, which nurse, which medical specialists are actually carrying out these activities for the patient. And this also becomes even more complicated if we start to look at the different patient profiles and their diagnosis report, the treatment plan later on. So what we like to bring up is that event log capture the process executions, which is a multi-dimensional temporal sequence data. And it is usually a result of infusion different data from different systems, for example, hospital information system, human HR system, so on and so forth. But then, of course, finally, it will be nicely pre-processed into a tabular looking, and we call this event log. And the event attributes are the column names, and each of this row represents one event. And the different events, they will correlate strongly with each other as if they belong to the same patient ID, representing the same process instance or same hospital episode. So then what we do is that we feed this data, event log, into a process mining tool, or there are already quite well-established process mining techniques that for us to answer these kind of research analysis questions. For example, what is the actual process behind? And we call that process discovery. And we also want to understand some of the behavior part of the process, behavioral part, for example, how many variants are this process more spaghetti-like or more structured, or what's the frequency, pass, and what will be the bottleneck. bottleneck, and then performance analysis to do with how efficient, how effective, how expensive or cheap, or how many errors they make. And then the diagnosis of processes, why some instances they are underperforming. Is that because of the bottleneck? Is that some of the resources are overloaded? And we call this diagnosis analysis. And we can also look at the conformance checking, so that if we have a regulation, then we can, and policies, then we can actually compare these what we discovered against those regulations, and we call that conformance checking, just to find, you know, the compliance and probably some of the deviations. So predictive process analytics take a step further to looking at more like a real-time process monitoring. And so we take an event log, but the idea of making them a spaghetti-like sequences is that the way to train a process predictor is to unfold all the complete sequences in the event log, unfold them into ongoing sequences step by step, so that we can use this ongoing involvement of the processes, instances, to train a machine learning or deep learning model, so that after we have the trained model, and of course tested, and then once we have developed such a model, then we can take the real-time ongoing process sequences or instances, and then to make certain predictions. And what kind of predictions that we can make is that we can predict what will be the next step. So for now we have 3 activities completed, and then what will be the 4th activity, and then when the process will complete. So what will be the remaining time from now on? What will be the remaining execution sequences of activities? Who will be executing the next activities most likely, and what will be the outcome process? So will this long application be accepted or rejected? To generate process predictions, it goes through, again, data processing, and the feature encoding and the predictive with machine learning model. And finally, we look at accuracy and precision of that model to tell whether the model is good or bad. So no surprise, but again, of course, with the process prediction, then as we said, we extract the prefixes, which is to then take the ongoing prefixes with different lengths and maybe put them into the different buckets, so that we treat the processes with a different prefix lengths differently, and train different classifiers or regression models for them. And we do the feature encoding and make a prediction. The question is that the accuracy of the prediction nowadays is not enough. We want to understand why such prediction, what features has made impact on that prediction. So we would like to generate explanations, and in particular, we're interested to understand what was used to make a prediction, and how these certain features or variables contribute to a prediction. Can we really trust them, and then to even move on whether there will be an error or something in the prediction path? So to generate explanations, we look at existing methods in XAI. And there are pretty much 3 different paradigms in XAI in terms of generating explanations. So first, interpretable model, it's basically a white box, decision tree or log-it regression. And we have there's also intrinsic interpretation approach, which is actually very much underexplored. And the idea here is to go into the black box, for example, deep neural network, and try to extract some level of interpretation. For example, with a deep neural network, with the attention mechanisms, we can somehow extract the feature weights during this learning process. But of course, that will at the same time affect the prediction performance of that black box. And the third mechanism, which is at the moment majority of the methods that we can find in XAI, is called post-hoc interpretation. And the idea is that we just leave the black box as it is and make it intact, and then we come up with a third-party interpretable model, usually a white box model, to mimic the behavior of black box, and by computing approximation of black box on every local particular data point. So here the emphasis is to generate local interpretations in this post-hoc interpretation. 2 widely applied techniques here. One is LIME, stand for linear interpretable model agnostic explanation. And it is the principle is to use a linear model to compute approximations of a local data point of a black box. And the other one is called SHAP. And this is based on totally different principle of using game series and to compute Shapley values. And for our current work, we look at LIME. As we found that LIME is more user-friendly, where it looks at the feature attribution that it provides, we can immediately map it back to the contextual knowledge or the interpretation of these features, where in the Shapley value is will need to be mapped onto the corresponding business interpretation of those features. So what then we do is that we take the post-hoc. Okay, so let me just maybe skip this details of there are different mechanisms for bucketing, different mechanisms for encoding, and the idea is some of them are quite lossy but more efficient. Some of them are very towards lossless encoding but very complicated. And then we also have the predictive models, which most of them are like the tree ensembles. And then we use a post-hoc interpretation method, for example, LIME, to generate interpretations, and based on what LIME can generate, and it's look at the feature attribution as the interpretation, then it will help us to understand or answer the question of which features are used for prediction and to what extent. Because the LIME did also give the quantification of how much that feature contributed to a prediction. Then based on this interpretation, we can then try to understand what are these different mechanisms of bucketing and encoding, and even the machine learning model themselves make a difference or having different impact on the prediction results. And we can use this information to do model debugging. And we believe that it is important to build a good level of confidence in the robustness and reliability of these underlying models, predictive models, before we can move on to generate user-centric explanations, which will be, again, which of course will be more appreciated by the end users and by the business users. So in our paper, we look at these different data sets. They're all publicly available. One is from a hospital process, one is for a loan application business process, and the other one is more for a government municipality process. And all the code and experiment that are available from our GitHub repository. So we did some quite interesting analysis and had very interesting findings, but here I'm not going to every detail of them. I just showed two examples of this, and hopefully to hide some of the technical details. So first analysis that we do is that we want to understand the relevance of these features, or to be more precise, the feature, how relevant these features are to the context of the event log or the process. So what we are looking at is that we look at a process trace of fixed prefix length 5, means that in that ongoing process instance, 5 activities has passed in that loan application process. And the LIME tells us that I believe this is to predict an accepted loan result, is that these are the top 6 features that are making the important impact on the result. Of course, the first one is giving a positive impact on the result, where all of the others giving a negative impact. But all of them are important features in terms of the influence on the prediction results. Then we would like to understand whether these make sense. Of course, with the public available data sets, we will not have chance to go back to the stakeholders to talk with them whether they make sense. So then what we did, we tried to use the existing analysis or mining techniques to extract the contextual knowledge or relevant knowledge that can help us to analyze, to understand how relevant these features are. So what we first look at is that we look at the global explanation generated by XGBoost, and it points out these top 6 features, which if we compare these two sets, they quite aligned with each other. Of course, the global features doesn't tell us about the value of these activities, where the LIME tell us that the non-occurrence of these 2 activities made an impact on the results. So we went further to the event log, and what we did, we just did a simple statistical analysis of the event log, and we look at these 6 activities, and we come up with a distribution of the occurrences of traces involving the 6 top activities. And what we found is that none of these 6 activities will occur in a process trace of fixed length less than 14. So this means that if we have a trace of fixed prefix length 5, which is less than 14, none of these activities will occur will not occur in any of these traces. So this then we come back to look at this result of the interpretation, and it's quite suspicious because these 4 features are actually applied to all the sequences, all the traces of prefix length 5, and why it is so particularly important for this prediction. So that leads to doubts clearly. Then we also look at the trace of prefix length 25, means 20 activities has already passed. And then what we look at is clearly the top 3 activity non-occurrence of this activity makes sense. They are reasonable as we look at the, more than 20, more than 14, then we would actually see these activities occurring. And we also look at this particular activity, and the occurrence of these particular activities, send back complete, will make a positive impact on the result. And we look at the process model, which is generated by a process mining tool. And we look at, okay, this is the activity actually just in this abstract view level, it just precedes the accepted outcome. So then it is also a reasonable and relevant feature. So the second analysis is also quite interesting, that we actually identify the data leakage through the explanations from the predictive models. I'm not going into the great details, but what we found that one of the outcome prediction using these 2 activity labels as in a predicate, and from the global explanations, we found both of them rate this, tells us that this AWB45 activity being the most important feature impacted the result. And we look at, again, the process graph generated from the process mining tool. And we found that this activity, 68% of the chance, this activity will definitely lead to a part of the information in the outcome. So this highly correlated feature used in the for the prediction, and it's a quite obvious indication of an issue of data leakage. So based on this result, we are currently work in progress on proposing a systematic approach for model inspection in the context of process predictive analytics. And clearly, as we can see, and as we can learn, that only rely on the interpretation is one important input. At the same time, we need another important input of domain knowledge or any process contextual knowledge that we might be able to extract from certain descriptive analysis. So next step is, let's say that so far what we've gone through, what we look at is that we get the explanations very much focused on feature attribution. So we would like to know why certain things happen. And ideally, we also want to know how the decisions are made. So then now it will be our next topic, and I'll hand over to Catarina.
So yes, so currently Lyman Sharp, they tell us what are the main features, but again, they do not tell us the why and the how. And in addition to that, we were also very curious because, again, if you know neural networks, so we have here a demonstration that if you have 2 features that are fed into a neural network, you can see that these 2 features, when they move to the first hidden layer, they become a function highly correlated. So it's simply a linear combination of features and weights. So just moving from the first hidden layer, we lose the feature. It's no longer the individual feature anymore. And the process repeats when it moves to the second node of the hidden layer or the third node of the hidden layer, or even when we try to go to the output layer. So what neural networks do, they are simply an optimization problem that try to minimize an error function. And again, when we have explanations like LIME that show the individual feature importance to the user, we started to question how can this be an explanation if, again, in a black box, we lose the feature. We do not understand what is the feature anymore because the output is given as a linear combination of features and weights. So that leads us to, again, the question, how can highly correlated features inside the black box be explained individually by features? And the answer is they can't, or at least they shouldn't. And this motivated us to start to think about another model to interpret features. And this is pretty much inspired in human beings. So human beings I can also not open the brain of a person and try to see what the person is thinking, right? But what I can do is I can provide some stimulus and I can try to see how the person reacts towards those stimulus. And from that, I can then try to build models that try to explain why the person decided to buy a car or not. And again, it is not one feature, it's a full set of features that are together playing a role in this decision. So again, life is uncertainty. Actually, I would dare to say that the ability to reason under uncertainty is the true hallmark of intelligence. And that is what we are aiming at. We do not want models that tell us how each individual feature performs. We want still this uncertainty to be present, so it would allow some reasoning process. So what we do is we have a black box, which again, we don't know how it works, but we can try to get some understandings where these data points that we want to explain fall in certain decision boundaries. And again, by providing this stimulus, we can actually then try to come up with statistical models or probabilistic models that can tell us not how one feature impacted the class, but how this full set of features contributed. So how does Linda work? So we start, it's a traditional post-hoc method where we start with an input vector. This input vector is then, again, the idea that I'm providing some stimulus that deviates slightly from this input value that are then given to the black box to see how the black box reacts. And this will allow us to have a new set of features that are completely labeled by the black box. Now, the hypothesis here is the following. If the point is in a very well-defined region of the space, then the permutated inputs should show very slight deviations from the class. And this would allow us then to build some probabilistic graphical models that can tell us how each feature is conditionally independent or dependent on this class variable. And this is what we've done by creating this local approximate inference and this local interpretable Bayesian network. So the good thing about this model is that it allows us to quantify in a certain level the uncertainties through 4 rules that we found. So if the data point falls in a very clear defined region of the decision space of the black box, then you will see that the explainable model is fully confident and will tell you how and why it's fully confident. It will tell you what are the features that are playing a role, how they interact, and how they are influencing the class variable. And the domain expert can then intervene and try to understand if this makes sense or not. But in these scenarios, again, what the result would be, the explanation is highly confident that this prediction is fine. So it would allow the user to trust this prediction. You would have scenarios that, for instance, the model would learn a class that is completely independent from the features. And again, this is a completely unrealistic scenario because it suggests that the black box was not able to generalize well for this particular data point. It pretty much means it doesn't matter what your features are, you always have a certain disease or you never have a certain disease, right? So it's the unreliability of the prediction. You can also have situations where actually the class, as you can see here, it's not certain. Actually, it's full of uncertainty and it's actually contradicting what the black box was saying. And again, we are not saying that this is a misclassification, but we can actually alert the user saying, please be careful because this data point falls in a very sensitive region of the decision space, which means that it can be susceptible to some bias or to some errors in some exams that we've done to the patient, for instance, and so on. So please recheck the features that you've done to see if they are correct before making a decision. And we can also have situations where the prediction is as good as flipping a coin. So the explanation couldn't actually favor either one class or another, which again suggests that the data point falls in a very sensitive region of the decision space. And again, the particularity in here is that the class was actually learned as a prior to influence the features. which again, it could allow us to reason, and then a domain expert could try to understand if this makes sense or not. So let's try to see this in action. So the high confidence prediction in a diabetes dataset, I guess everybody knows this dataset is a very well dataset from the literature. You see that, for instance, slime here simply tells me what are the main features that are playing role here. While in here, in our approach, we actually not only have a full confidence that the explanation is or the prediction is okay, but also how each feature is impacting this class. And we can even explore features from Bayesian networks like conditional independence, which would mean that knowing the value of this feature here will make all these features conditionally independent from the class. So it means that only these features here are actually playing a role in the prediction. We also came up with examples that, for instance, we had the diabetes completely independent from the class, which again, doesn't matter if the person has high glucose levels or low glucose levels, the person is deemed to always have diabetes, right? And in Lyme, we cannot have this understanding. Actually, this is a false positive, as you can see. In here, we can actually spot that something wrong happened. In Lyme and SHOP, we do not have that knowledge. And again, we can continue and see again the other effects contrasting the class, and we can see the main features, the uncertainty in each feature during the permutation process. While in here, again, we just know that certain features contributed to the class and others did not. And again, the scenario where we have here the prediction, which is as good as flipping a coin in terms of the explanation, which suggests again that sensitivity in the decision boundary. So what are the advantages or the new possibilities of using such approach in XAI? Well, again, this is just in their initial stages. There's still a lot of work to do here. But here, again, we have lots of ideas of such a structure, because this can allow us to try to extract reports out of such structures. So one open research question is in the field is precisely how can we map this sub-symbolic information of interpretable models to human understandable explanations. And when I mean human understandable explanations, they need to be human-centric. They need to adapt to the user that they are referred to. If I'm explaining something to a patient, it's not the same time of explanation to a doctor, right? So by having the conditional independence, by exploring the uncertainties in the node, we can actually come up with the reports that can be extracted, or at least have the potential to be extracted out of these features to give human understandable explanations. This probabilistic acyclic graphical model can also open us some doors to causation. So again, the problem with these interpretable models is that they just say features that are correlated. But again, this correlation can even imply more biases, even in the explanation. So causality would actually be the ultimate outcome for an XAI system, because right there we know which features actually contributed to cause a certain prediction. And as in Pearl said, we have here the different levels of causality through the ladder of causality. Association is the one that is more connected with our approach. So it's the normal probabilistic inference. So it's the level 1. And the important thing here is to mention is that in terms of causality, so causality is probably the biggest revolution that we have seen in data science in the last 20 years. And the revolution here comes from this shift that the knowledge does not rely on the data itself, but rather on the underlying processes that generated this data. So we humans are simply observing a data that has been the process or the output of some processes that are given by nature, right? So they are unobserved to the user. We can only see the outputs. And Pearl developed all these mechanisms from different levels, depending on the type of query that we want to make to our system in order to try to understand causality, how each feature is actually impacting a class. And although we have here interventions through the do calculus, which are more predictive in looking into the future, what if I do this, what will happen? When we are in the domain of XAI, the only possible causal analysis that we can do, in my opinion, is the counterfactual one. Because again, counterfactuals is more, what if I had done something? What would have had happened, right? So it's something, it's imagining. It's from already observed data. Is it possible to infer from a hypothetical scenario what would have happened if I had taken another action? And given that in XAI, we already have all the observed data. I mean, in data science, the data is already there. It has been already collected. The way to proceed, in my opinion, would be through the generation of counterfactuals, which again, the probabilistic graphical model can serve as a basis to try to come up with the bridge, the big bridge and the big gap to achieve counterfactual. And it's not just me saying, it's actually the literature saying that we need to move towards these counterfactual inferences. So again, we see that in the initial years, everything is a machine based on a statistical analysis, treatment outcome. And then we start to incorporate the humans with, again, risk factors, risk assessment, social economical factors. And again, the counterfactual here is the bridge between the humans, or these causal inferences in humans, and these automated approaches that are now in machine learning and explainable AI. So we are seeing a clear shift in interest in the literature moving towards this direction. Let's see a demo of this working. So for instance, in our model, you can see, for instance, we have here a neural network with a certain amount of hidden layers. And we can simply try to predict or explain why this patient here was predicted diabetes. It was actually a true prediction. He also actually had diabetes. And we simply can generate the explanation. And we not only have the probabilistic graph, we can also see the uncertainty, the graph in terms of uncertainty. We can have the Markov blanket with the main variables. And the great thing is we can export this explanation network and actually interact with it. Well, the idea would be to have all this centralized in one framework, but for now we are playing around with the additional software that would allow us for a domain expert to say, no, there's a feature here that is wrong, and how everything would be affected. We also have, for instance, the ability to generate, again, reports from this type of explanations and so on. We can also have the case where, for instance, we have the other rule. Actually, it's the other video. It's this one here, where we have, for instance, a false negative, and we want to try to understand if we get any insights. So the prediction is not diabetes, but where in fact it should be diabetes. We generate our network. We see that there are some uncertainty in the features. We can again interact with the application. And the domain experts can say, no, what actually is observed, because the permutations can shift a lot, these boundaries. You can somehow try to align better the exam results of the patient and look what's happening to diabetes. It changed, maybe we can see that happening back again. It changed from a no, a 71% in no, to, I need to start to resume. So when we started to incorporate knowledge, it started to decrease and actually support more the correct diagnosis. So again, this probabilistic model that was learned near the decision boundary can actually help us refine and gain more knowledge about the behavior of the system. So I pass to Chun now about the open research questions.
Yeah, thank you, Kat. So now let's, so it's a highly impacted talk, and then let's now wrap this up with some of the open research challenges. So what we also move on from now is that we are interested to know that how an intrinsic method will look like, especially if we have the deep learning models, what kind of attention mechanisms or even the transformers later on, the techniques, how that can help us with extract some of the interpretations from the model, but at the same time, we understand getting that, supporting that interpretability may sacrifice or compromise the accuracy, and what will be the trade-off. So the second point, of course, when we have more than one evaluation, explainable methods, and then the alternative ways to generate these explanations, post-hoc, intrinsic, or even different methods in post-hoc, how can we tell which one is good than the other? So what will be the evaluation metrics? For example, in the post-hoc method paradigm, how faithful the explanation is given as compared to the black box, because we're using third-party model. And then in the intrinsic method, what will be the trade-off between accuracy and interpretability, for example? But there's also measures of interpretability and explainability that needs to be also defined and confirmed. Then the third one is very much follow from the first topic about what would be a systematic approach look like for model inspection, so that it will lead on to the support for model robustness as well as reliability. And if now we're all familiar with the classical evaluation for accuracy, precision, F1 score, do we have the measures for model reliability? And then how do we promote the causality in explainable AI systems is very much based on what Catarina has talked about. And how do we support not just the explanations, one type of explanation or the understandable explanation, how do we generate persuasive explanations given the different cohort of end users to set so that, you know, we put in the context, build the right representation layers, so on and so forth. So again, the list is definitely not finishing here. There's more to do, but this leads us to the work ahead. And we have also publication reports that we'd like to share with you. And all of this you can also access from the archive. They're all available for open access from archive. And that leads to the end. And we now like to open the floor for questions.
Thank you.
Thank you.
Thank you so much, Chun. Thank you so much, Catarina. That was an excellent talk, and I see already prompted some questions in the chat box. So we have about 14 minutes, very well-timed talk. Question and discussions. I would note that we have a breadth of researchers and industry and governmental organisation representatives here today, and included amongst those we have from industry data scientists, engineers who are, you know, dealing with the issue of explainability to their industry clients, and also representatives from our national statistical organisation, who of course, you know, the issue of explainability and trust in their work and their statistics is of vital importance. So they're here as well. So there's a really great opportunity for knowledge exchange as there are these open questions. So I do want to give our industry and government guests an opportunity to ask any questions that they may have. So please feel free to put your hand up or type it in the chat box, unmute yourself.